This blue screen.
Oh, okay.
Maybe I was watching that.
Okay, it's worse. Okay, okay, very good. So, well, good afternoon, everybody. Is it working, the audio? All good?
Yes.
All right.
Maybe I close this one. No.
Okay, good. Thank you, everybody, for the invitation. So, as I said, today I would like to give you an introduction to superconducting qubits, which is a sector of quantum computing, and in particular what we do at DeFi in the QCT group, Quantum Computing Technology Group. It's a very broad topic, so it's going to be very general, but I hope I can give you all the information so you can understand what I showed you at the end. And then as a backup, I have some measurements we do in the lab. I couldn't fit it because it's too long, but then if you're curious, I can show the measurements we do. Okay. So as a short personal presentation, I did my PhD in Max Planck Institute for Physics in Munich, and I actually was a particle physicist in the PhD, and I specialize in cryogenic particle detectors. And cryogenic is the field that bridges, let's say, what I was doing as a PhD and what I'm doing as a postdoc now. I started my postdoc in 2021 here at DeFi, and I'm still there. And there we focus on many projects involving superconducting qubit technologies. The PI of the QCT group is Paul Fordiaz, that you might know. He's an expert in superconducting qubits and quantum optics. He's actually from Catalonia, but he went a bit everywhere in the US and Canada for the postdoc. And he came back and started the QCT group in 2020, and in particular with a big project that is called Abacus, which is a European funded project. And also outside academia, he co-founded the Kilimanjaro Quantum Tech, that you might know. It's a startup, but it's actually getting quite big. And we have also another senior researcher, who is Manel Martinez, who's specializing in gamma ray astronomy. And now we have two generations of PhD students in the lab. One is finishing, one is starting. So right now we have 5 PhD students, but we will go down to 3 soon. And then, so the first time I gave a seminar that is an introduction, I realized I don't know anything about computation. I mean, I'm a particle physicist that I do quantum computing. I don't know anything about computation. And then I started reading, and I was like, wow, this is very similar to the problem we're facing now, because classical computing, if you go look into history, is not a thing that just came out of nowhere. It took many years. It took many people, different technologies evolved, and in fact, if you want to look what is the first computer, it might be this mechanical system with no electricity that was invented in ancient Greek and was predicting, I think, astronomical events quite accurately, apparently. And then the first programmable electronic computer is 1945, and it was using vacuum tubes. And we do not use vacuum tubes anymore. Okay? We use transistors, and in fact, we even have the 8th most powerful supercomputer in the world in Barcelona. So, wait, is it the wrong one? Oh, yes, it's a lot. Okay, so the reason why we can also have different technologies, the base of computing, digital computing, is Boolean logic. So it's quite a simple concept in the sense that you want a true or false, so a 1 or 0. And if you want to implement this in a hardware, it's simple, it's a switch. Okay? So what we do normally, if we want a switch, we have, for example, the current is flowing, or the current is a 1, or the current is not flowing between two spots, and it's a 0. And this could have been done with a vacuum tube. In fact, we started doing it with a vacuum tube, not me, but we started doing it with a vacuum tube. And now we transition to a transistor because it is much more efficient. You can pack more, you can make more chips in a smaller geometry and many other advantages. But in the end, it is current flowing between two spots, two points. And then in 1982, Feynman put out a paper saying, well, if you want to do If you want to calculate quantum mechanical phenomena, we should maybe use quantum computers. We should maybe use quantum computers because it will be more practical. So that, well, that is up to for debate because yes, in the ideal form in the theory, yes, it's better to perform a quantum computation with the quantum computer. But then in practical form, well, we're still here that we're still struggling with it. But the point is that if you want a quantum computer, you have to rethink more or less all the basics of computation. Okay, because a quantum computer function with a classic bit that is usually predetermined in the hardware, so it's a 0 or a 1, as we just said, it's a switch. And instead, the fundamental unit of quantum computation, which is a qubit, does not work like that. It works like in a superposition of states, and you don't have a predetermined state. In fact, if you want to just bring home one concept for today, is what I will say this is the most important. So what is a qubit? Because a qubit is simply a quantum mechanical system that has two states, two levels, whatever you want to call it. Okay, and that's it. So you can, it's agnostic regarding to the technology, like a transistor or a Bakken qubit, because it has just to be quantum mechanically and have two states, which we usually call fundamental or ground state and excited state. Okay, so as I said, the qubit lives in a superposition of states. You can have a geometrical representation that is called log sphere, and here you can have two basis vectors that we can call 0 and 1. And if you want to go back to classical bits from a qubit geometrical representation, conventionally we pick it as two poles of the z-axis. Okay, so a classical bit lives only in these two states, while a qubit can go anywhere in this log sphere, it can take any angle, any direction, and so it's much more complicated than a classical bit. And then the other big property, of course, is entanglement or entangled states. In classical computing, straightforward, you think about every bit as an individual bit of information that is predetermined, and you confront, you do logic gates, all good. But then when you start talking about quantum mechanics, it's hard to assign an individual state. Actually, you cannot assign an individual state to qubits. For example, let's take two qubits, 1 and 2. We assume that one can take 1 or 0, and the other will take 1 or 0. But let's assume that in the whole system, yes. yeah. So let's assume that these two qubits, we assume that one takes the state 0, one takes state 1, but we perform a measurement to qubit 2. And what happens is that we should see that maybe qubit 2.
It's lag because it's slides are moving on this laptop, but not on that screen.
Yeah.
Maybe he can press the arrows directly.
No, it's
This is the internet. Okay. Well, let's move on. So basically, what it means that the qubit 1 or qubit 2 or qubit 1 can be in state 0 and 1. When you perform a measurement, you see if one is 0 and 1, and then automatically you know the other is in the opposite state. This is a classic entanglement example.
Okay.
What can I tell?
it's very strange because here it's completely changed.
This is clearly the internet of CBC.
Students collapse the internet.
It's Wi-Fi, not.
Okay, I tried the other Wi-Fi. Okay, now we have the.
All right. So as I said, you have a 50% probability that qubit 1 is 0 and qubit 2 is 1, or the opposite, that qubit 1 is 1 and qubit 2 is 0. So as I said, the qubit is quite agnostic regarding the technology. In fact, people figure out many ways to make it, from superconducting qubits to trapped ions, vacancies in diamonds.
See?
And so if you want to have a landscape of the quantum hardware, this someone made a nice chart. Every fine print is a group working on the problem, and you can see there is big areas of research. Superconducting is still by the biggest one, but there is many others that are quite big. And I mean, we do not know which technology is better. Today I'm just showing you the technology that pays me, essentially. But let's assume for a second that you have your qubits, I don't care how you made them, and you would like to perform some calculations. Then you have two strategies. You can do the gate-based quantum computing, also called digital quantum computing, or you can do the quantum annealing. You can approach with the quantum annealing concept, which is more similar. It's an analog quantum computing. So the gate-based quantum computing is very similar concept to the digital computation, but now you work with qubits and you work with different gates. You start to manipulate their state, and you can do many different logic gates. And this has some pros and cons. So the pros is that this is a universal approach. So it means that theoretically it is proven that you can solve any type of problem. Whatever type of problem you come up with, you can solve with this. The big problem is that it requires an enormous amount of qubits. Okay, so let's say you see this this timeline. More or less, we are here, 2023, 2025. So the best chips have around 1,000 qubits, maybe 100 qubits. So they are Google, IBM, this type of companies. If you just try to pack more and not improve substantially the technology, you will need 10 to the 6 to actually reach, or more, 10 to the 7, to really reach a working quantum computer. This because, of course, the single qubit is hard to control, information tend to be dispersed into the environment. So you actually need ancillary qubits to check that your qubit is actually performing what you think it's performing. And then you need ancillary qubit to check that the ancillary qubit are checking properly the qubit that is supposed to perform the operation. So let's say maybe in theoretical framework, the computation power of a quantum computer goes to 2 to the n. If you want to simulate all the atoms in the universe, you would need maybe 65 qubits. But then if you want qubits that work well, you need 1 million or 10 million.
What is this image?
This is the timeline of some IBM or someone.
Okay. But this guy in there?
Well, this is exactly, if you would like to scale the technology we have now, that is a chip of 1 centimeter maybe, and you want to put the 10 to the 6 with all the experimental infrastructure, you will have this scale. So it's basically a full room. Now you have, let's say, maybe a wardrobe size machine, and then it will be a full room. And yeah, this is crazy. I'm experimenting.
They cannot get smaller than 1 centimeter.
No, I mean, in 1 centimeter, you can fit 1,000. And then if you want 1 million, you can start build up, but then you have, I will show you later what you need to actually use a qubit, and you need all the infrastructure around it, and this will scale up. The wires, the cabling, it's a lot. So this is the approach to superconducting qubits with gate-based quantum computing. One of the most famous is Google, that made some controversial papers even in the past. And then the other approach is quantum annealing, which is quite niche, but it has the potential to be more useful in the short, medium term. This time you will not work with the logic gates, but you work with continuous functions. In this case, I'm not a theoretician, but let's say you start from an Hamiltonian that you know, and you would like to go to a final Hamiltonian, that is the problem you want to study. You can evolve the system adiabatically, so very slowly, with 2 factors in front of the 2 Hamiltonians, so that varies over time. So basically, you start fully with the initial Hamiltonian, but you slowly suppress it, and you basically increase the weight in the final Hamiltonian, and in the end, you perform a calculation. So this is more or less how it will work. The pros and cons of quantum annealing are different than the other approach. It is not universal. It can only solve the specific problems, like especially optimization problems, like traveling salesman problem, or find a global minimum, which is still quite a good skill, let's say. Requires a reasonable amount of qubits. I cannot quote how many, depends on how good they are, but it's also the other problem, let's say, is that they have to be interconnected quite well. This, as I said, is a fringe approach. You see, it's only a few people working on it, but it's our lab working on it. So, and Kilimanjaro, technically, will be like to work on it. And the most famous company is D-Wave, that makes a lot of qubits with the dubious quality. And that's, in fact, is what we are trying to do, is make less qubits, but with better quality, and see if we can find useful application of this. I say superconducting a lot, but I need to introduce you to the concept of superconductor. So a superconductor is simply a material that, when it's cooled below a certain critical temperature, exhibits no electrical resistance and expels the magnetic fields. Okay, the most basic definition I can give you. There are many materials, and usually the ones that are employed in superconducting qubits are aluminum, niobium, tantalum, titanium. These elements are used to produce thin films, let's say in the order of 10, 100 nanometers thickness, on silicon and sapphire wafers. And this should ring a bell because basically this is the semiconductor industry, more or less. And then I would like to introduce you to the transistor, let's say, of quantum computing, which is the Josephson junction. Okay, so the superconducting qubits have a fundamental basic element, which is this Josephson junction, which is just a sandwich of two superconducting layers with an insulator in between. And why this is important? Because this simple object is a relatively macroscopic object that behaves like a two-level quantum system, or that can behave like a two-level quantum system. In particular, the Josephson junction is a nonlinear, behaves like a nonlinear inductor. This means that you can, if you have an LC circuit, you can replace the inductor with a Josephson junction, and you will introduce an anharmonicity, which is very important because at this point you do not have the energy 0 and 1, 1 and 2, 2 and 3 are all the same, but 0 and 1 energy is different than 1 and 2 energy. So then you can isolate from ground and first excited state, and finally you have a two-level system. For the quantum system, you instead employ this other thing, which is the Josephson effect. This is a macroscopic quantum phenomenon, which means that if you build a Josephson junction, you will have a supercurrent, as it's called, that continuously flows across the junction without any voltage applied. So it can flow eternally, basically. And microscopically, this is enabled by the tunneling of Cooper pairs, which, well, in superconductor, you can look at BCS theory. This is another hour presentation, probably. But you have that a certain, so the electrons start to pair, they form Cooper pairs, now they behave like bosons, more or less, and they can tunnel through the insulating barrier in your Josephson junction, and this is the origin of the supercurrent. So I got away with saying relatively macroscopic object for the Josephson junction. I would like to give you some sizes. Okay, this is a chip that we have in our lab. It's 1 centimeter of lateral dimension. And well, even with the best phone, it's going to be very hard to see a Josephson junction. But let's try it. If you look close to the chip, you can see some features already. So you have a feed line, where we send input and output signals. And also we have some flux lines that are used to control locally the magnetic field, or to send locally some pulses to the qubit. But there is no way you can see a Josephson junction, and not even with the most zoom you can try. But you can go with the optical microscope and you start to see more features. So this is again the feed line. This more or less is where our qubit is. This is the flux line I showed you before. So this part here, and this is the resonator. Every qubit has a resonator, but I will get to that later. And you can still zoom even in optical microscope, and there is no chance until you really zoom a lot and you start to see the qubit loop. So here I lost completely any resolution in my picture. And it's not very focused, but you can start seeing the Josephson junction. This is the Josephson junction. And then if you ditch the photons and you start using electrons for your microscope, you finally see it. And the lateral dimension of this is around 300 nanometers. So it's a very tiny structure. And we found the junction. As additional headache is that the Josephson junction is three-dimensional. It's a 3D structure. It's not only a planar, which means that usually as we do it is we put an aluminum layer, an aluminum oxide layer, and another aluminum layer. And roughly this insulator is around 10 nanometers. Then you can go to Wikipedia, look at aluminum atom, how big it is. And I made a quick calculation, and it will fit around 30 atoms, something like that. And this is a problem because the smoothness of the interface between aluminum and aluminum oxide, also the homogeneity, the impurities, the defects, is a limit in the quality of superconducting qubits. So you really have to go very close to the atomic scale in the manipulation of your hardware to be able to make good quality qubits. And usually when we talk about computers, we usually have transistors. As I said before, the first thing is that you put the 1 and 0 and you're reasonably expecting that it stays 1 and 0. But qubits don't work like this, okay? There is a thing that is called quantum coherence if you want to be optimist and you want to see the glass half full, or quantum decoherence if you want to be pessimist and see the glass half empty. And it's basically the loss of information to the environment. So this is a measurement I did myself in the lab. I had a qubit. I excited the qubit with a pulse that I know will bring it to the excited state. Then I waited some time. This is an average measurement, of course. But I waited for some time, and you see that after 200 microseconds, there is no way that it is excited anymore. Its probability goes to 0. So this means that you lose information quite fast in the environment. And there is many sources of decoherence. I will show you a few of them. But first, let me show you this. So in the block sphere, this is how it looks like. So you would excite it and then relax, and this will be what I show you. But also you have the phasing. So not only it relaxes, but you kind of have this precession of the vector. So this is important because, for example, in gate-based computation, you have to apply many gates, and you want also to keep your phase constant. You don't only want to keep your energy constant. And so let's talk about some source of decoherence, which the biggest one is called two-level systems. And I will try to explain as straightforwardly as I can. This is the main limiting factor. And it has to do with the defects of interfaces and materials, leftover chemicals, impurities, etc. So you can imagine like this. You are creating a two-level quantum mechanical system that you want. But in the process of making that, you create a lot of unwanted two-level quantum mechanical system, which, I mean, all the atoms in the end and many chemicals and many molecules will behave like that, many defects, traps in the semiconductors, etc. So essentially, your qubit can start interacting with all the unwanted qubits you're making in the process of fabrication and loses information. And it can start losing information to what is the environment. Then there is thermal excitation. For this, we have a good answer, which is called a dilution refrigerator or cryostat, which is my area of expertise. This instrument cools down the superconducting circuits below their TC, but the job is not done there. It's not only that you have to go to TC, but much lower, so you can minimize the thermal excitation. And in fact, you can see here, for example, in these two plots, this is the initial state. So all the qubits are cooled down and are in the ground state, and then they get excited with the pulse. And you see that it's never 100%. So you always have the chance that some qubits are excited even in the ground state. These effects are much worse if you don't thermalize well your qubits and your qubits are warmer rather than cold.
I need to ask something.
Yes.
Can I?
Yes.
This sort of tomography in the quadratures and whatever, what does it mean? Like, what are you measuring?
So here I think you're repeating many measurements to check where the qubit is. So
Okay.
if it is in grounded excited state.
But you saw, for example, you have 4 Josephson.
Yeah, so consider that one qubit can be made of many Josephson junctions. It doesn't
Okay.
have to be one.
Okay.
So let's assume you just have a qubit as 2 levels. No, you can start probing the qubit and ask the qubit, where are you? Are you in this ground state or excited state? So normally the way it works is that you have everything cooled down. So everything should be at the ground state. Okay? But then, as you see, there is a 3% that is not a ground state, even if you in this measure. Then you want to excite it, and in theory everything should get excited, but well, it doesn't work always like that, because some can decay earlier or some can be in a weird phase of transition between the 2 states. But in general now, the state-of-the-art qubits are pretty good. They have a high fidelity, what is called, it's the 99, 95, quite high. Then another source of decoherence, which is my, let's say, area of expertise, especially is ionizing radiation. Ionizing radiation is everywhere. So you have cosmic rays, you have radioactive elements, you have whatever, everything. And this is important because, as I said before, this supercurrent is enabled by the Cooper pairs. And the Cooper pairs have a binding energy, which is around 340 microelectronvolt in aluminum. So a visible photon has 4 electron volt, more or less, so many orders of magnitude higher. So you have to take into account the ionized radiation when you make your superconducting qubits, because they will destroy easily Cooper pairs. And one of the bad things for digital quantum computing is that they provide correlated errors. So when you have ancillary qubits checking your qubits, etc., you would like that you have uncorrelated errors, so your techniques for correction work. But ionizing radiation tend to disrupt all the qubits at the same time, so they are not uncorrelated anymore, because they actually also quite geographically concentrated. Anyway, I'm going to go a bit faster. So this is our lab. We have one dilution refrigerator. We have a metal evaporator to make qubits. We have a small clean room, probe station to check the chips, and we have the control electronics to actually perform measurements. And this is our dilution refrigerator. So here there is the stage that is at 300 Kelvin, or well, whatever the room temperature is, let's say. And then we have a stage that is at 50 Kelvin, 4 Kelvin, and then we go down to 1 Kelvin, which is quite important. It's minus 272 Celsius, but it's important because it's below the superconductivity of aluminum. So it's the first stage where things actually get superconducting. And then we have the last stage, which is actually 20 millikelvin, which is
really cold.
Which is the very cold stage, which is basically absolute zero, and is where we install our samples. In fact, this is a qubit sample as showing here. And actually, well, to show all the process, you take the chip, you put the chip in a PCB, you put the PCB in a box, you put the box in the last stage of the dilution refrigerator, then you put, which is this stage, and then you start putting shields to avoid the black body radiation and to shield from magnetic field. And then finally, you put it in a can and you put it in high vacuum environment, which is about 10 to the minus 9 atmosphere. If mine doesn't work in millibar like mine, because I basically use only millibar now. This is actually this if you make a scheme. Okay, so this is all electronics and stuff. I will not go into details. If you're more curious, we can go later into the details of this. And so let's assume we have an instrument that is called Vector Network Analyzer, VNA for short, and we want to have a look at our device. So you can start sending an impulse from this input port of the device. It goes inside the fridge, it reaches your device, and then it goes through the feed line. And actually I'm lying, because I show you a device without electrical connection, but this is not how it works. You actually have to provide electrical connection. We do this with what's called a wire bonder, which is you basically have to do it manually with a microscope and provide electrical connections to the feed line, otherwise it would not work. Anyway, we go back. So the signal comes out of the device, is amplified, filtered, blah, blah, and then finally it arrives to your instrument and you start to see a signal, okay? And then usually what we do is this. So we usually now work with planar geometry, okay? So we have, in this device specifically, we have 8 qubits. Each qubit has a corresponding resonator. And so we work with microwave electronics. And you will see that each resonator has a characteristic frequency, which is a pole resonant frequency. And this frequency is given by the shape of the resonator. So it's purely geometrical. And this is important because let's assume you have 8 qubits. As I show you, you have only one feed line. How do you control qubit 1 or qubit 4? You need a resonator. You need to know that you can only excite one qubit if you put exactly the frequency of the specific resonator. Well, you can also do this wireless, which is quite fun. So you can actually use a 3D cavity. So it's just a box with like a microwave oven style cavity. And then you have your qubit here. This is actually the qubit. This is only silicon, but this is the qubit. It's very small. And this is very good because you have a very long coherence, but bad because it's bulky and it's very hard to scale up and then very hard to entangle. But it works. You can easily measure a qubit inside a cavity and it works very well. I think some people are thinking about using cavities as quantum memory because they're very good in general. So I also lied a bit because I only show you on one instrument, but actually what we do is a bit more complicated, especially when we want to actually start doing a more advanced calculation, advanced measurements. And actually we start from our classical computer here. And then we send through a software some instruction to arbitrary waveform generator, which makes our time domain pulses in the shape and form we want. And this then goes slowly inside your qubit, then it comes out, and then we digitalize the signal and then send it back to our classical computer, so where we can actually check what we're doing. So what I showed before is a basic, what is called spectroscopy, which is basically to assess if the qubit is alive or not. But when you want to do more advanced calculation, it's much more complicated, the whole electronic and software scheme. Now, I'm going to tell you a bit more what we do in our lab, and then if you want, I can show you a bit of measurements more. So the lab started essentially with this, which is a coherent annealers. So we are focused basically using this quantum annealing prototypes, and I think the goal is to, well, this project now is over, but the goal would be to go around five connected high coherent qubits to make these annealers. We are also invested in developing new materials to be used in superconducting qubits. In this case, we have a paper out where we made the first, let's say, measurement of thin films made with nitridized aluminum, which is aluminum that is deposited on silicon in an environment with a lot of nitrogen. Okay. Why this? Well, because usually the TC of aluminum is around 1.2 Kelvin, but these films have a much higher critical temperature, so they can have 2-3 Kelvin, and this is advantages for various applications. Also, they tend to be much more resilient to magnetic fields, which is also very relevant in the qubit technology for, again, various applications. And so the hope is that maybe we can replace, maybe not all, but some parts so that we make with aluminum now with the nitridized aluminum. And then we have a project which I think also just finished, which was an ultra-strong coupling project. So these, so I'm not super involved in this, but it basically they want to probe what is called ultra-strong coupling regime. And so the idea is that using qubits you can engineer artificial atoms, and you can use superconductor materials like nitridized aluminum that I just showed, to reach actually this ultra strong coupling region.
Can I ask, when you're saying engineering to level artificial atoms,
Yeah, so
what are you?
so in nature, you know, you have atoms, okay, but they never, I think they cannot reach this regime. So what you can do is you actually make it with metal. A qubit is basically an atom that you are engineering, and then you can use these very weird elements or weird materials that have very high inductance to reach exactly these very strong couplings, which it's hard to find in nature. So this is exactly why it's artificial. And then this is me working in the underground lab in Canfranc. We also have, we are assessing the impact of ionizing radiation superconducting qubits. And we would like to, I mean, we are working on radiation suppression. So with shielding or on-chip structures that allow us to reduce the detrimental effect of ionizing radiation. And we actually have a project with CNM around here and Canfranc. And then we have also some future projects, which is one is called QRADES, which is so superconducting qubits are affected by ionizing radiation, but then you can flip the script and say, okay, ionizing radiation can be sensed by superconducting qubits, and in fact, people have started to use superconducting qubits as axion detection, so dark matter detection, and this is the project we will do in the next year, that we will try to do some axion detection with superconducting qubits. And in the end, you might have heard the news recently, we are also involved in the Euro QCS, which is this Barcelona Supercomputing Center will build a quantum annealer. They have already two, let's say, digital quantum computers. They will build an analog quantum computer. And IFI will provide technical expertise, in particular in benchmarking the quality of the quantum processor that will be delivered. This is still, I mean, there is a lot of way to benchmark digital quantum processor, but not many ways to benchmark analog quantum processors. So we will have a student working on this. And I think this is all.
Cool. Where is it Canfranc facility?
It's in the Pyrenees.
Is it Canfranc?
Yeah, in the station, the old station. Yeah,
Okay.
in the tunnel, the old tunnel of.
So it's because it's underground, right? You need it for more shelter.
Yes, it basically does. You don't have cosmic rays. It basically the suppression is 10 to the 6.
But you can suppress all ionizing radiation?
No, cosmic rays.
Okay.
Then you have to make shields to suppress ionizing radiation, but you can achieve very low levels, especially for small chips, because I mean, okay, if you have a large volume, but this chip is so small, so you can really physically see no radiation.
I have a question. Sorry, it's speculative. I'm not listening. But a year or two ago, I was following about this LK99 drug.
Which one?
So the LK99, the room temperature superconductor.
Ah, okay, yes.
And it didn't turn up, but people at the time were telling stories about how it's a game changer. How much of this becomes easier, and how much easier if there is a big breakthrough in superconducting materials and things acid cooling?
It gets much easier, but I'm not sure. I mean, it's not only the, well, of course it gets much easier because it will teach most of the cryostats and most of the infrastructure, but then.
Stuff is still a problem.
Huh?
The cosmic rays and stuff.
Yeah, but this is okay. Okay, there is scales of problems. So the biggest problem is the quality of materials. And these, okay, you can invent a room temperature superconductor, but then it has to work properly. It doesn't have to have a lot of losses, it has to be good. Like, so I'm not sure how much it will work because, as I said, we are using state-of-the-art fabrication that is used in semiconductor facilities. Mostly. They are not fully compatible, but they are very close. So we are using machines that are insane. When you go to look into the details of how this machine works, they are very expensive, very sophisticated, and still we have problems with the quality of the aluminum, which is widely used everywhere. So sure, some materials science will be needed if you want to go to this route, and this will be better if it is a higher critical temperature material for sure, but I'm not sure in the end if it will solve all the problems. It will solve some problems for sure. And then, I mean, when you were saying, oh, why the room? Like, you know, this, I don't know if I have a picture. Maybe I can go to the backup because I have some. Okay, this is 1 qubit. So this is a box that can fit in my hand, and it's 1 qubit. Okay, so okay, this is a cavity, is a very specific measurement, is a very specific approach. But then even a chip, okay, the chip is small, but the cables are not. So you can see the size of a cable is not negligible. This is a filters, and this is the passive component. And then, okay, now the fridges, the cars we use are insanely developed compared to the one in the 70s, the 80s. But I mean, if you want 1 million of cables and 1 million of filters, this gets out of hand pretty quickly. And then you also have someone that has to connect 1 million cables, which is another problem with this. Okay, so I don't know if there is any questions.
I have a lot of questions.
Okay.
Well, first, thank you. Super cool. Like, really, yeah, well, but it's cool. So, I mean, I don't know how involved you are in this part of measuring the state of the qubit.
I do measurements. I don't. Yes,
I do measurements.
Yes, I do. Usually now we are at the level. So the lab started in 2020. There is a level where you start fabricating and you start checking that you are fabricating properly. We are at the level where we start having working qubits. So there is a part that you benchmark your qubits. So they see if they work, how coherent they are, and then there is a part where you start using qubits. So, for example, the annealer. So far, we work with prototypes to see if we can actually produce qubits that can be used in a quantum annealer. But we never went to the stage where we use a quantum annealer. So, for example, you do molecular. So these I wouldn't do. But there is people that are interested to run algorithms in quantum annealers.
I was a bit more referring. I don't know what experimentals mean by measuring.
Yeah, so I can show you. For example,
like getting these plots.
Yes. So these plots, I show you the instruments before in a scheme. Okay, so let's forget for a second the fridge because there is filtering, amplification, etc., etc. But then, for example, this is probably the easiest measurement you can do. Okay, you have a transmon qubit in a cavity, so completely wireless. You close it. You put an input and an output. No, and with the instrument I showed before, the one that sends the signal. No, you can start sending a scan of frequency around where you know that. This resonant cavity has the resonant frequency, which is here. No? This thing is 7 gigahertz, for example. And then you can send a power, and then you can start to increase the power. Okay? You will reach a point where you overwhelm the cavity with photons. And if there is a qubit, you will see an effect that will show that the cavity will change its resonant frequency. And this is exactly what is happening here. You reach a breaking point where you put so much power that the cavity jumps to another frequency, or here. So the difference between this and this is that here, the qubit has a frequency that is below the cavity. So the qubit here was, I don't know, 5 gigahertz. And here the qubit was higher than the cavity. It was made wrong, and it was 15 gigahertz or something. Okay. So this is just the direction where it jumps. But then if your qubit doesn't work, nothing happens. The cavity starts to lose. It gets distorted the resonant frequency because you're putting a lot of photons, but you do not see an effect. So this is I think the simplest measurement you can ever do because you need one instrument and you just change the power. Okay, but then you can get more sophisticated. So you can start using flux qubits, and these start to be more fun because I showed you the chip before. We had 8 qubits, no? So to check if a flux qubit is alive, in this case, you modify the magnetic field. And you will start to see what is called avoided level crossing. So this very sharp feature here that is symmetric and has a center, which is called the sweet spot. In this case, you know where the qubit is. So let's say you don't know where the qubit is, but you know where the resonator of your qubit is. So you send a range of frequency around your resonator, which is this Y scale, and you start modifying with a coil. Actually, I have so this is a coil. It's just a really winding of a wire around the cylinder. You start modifying the environment very close to the qubit so that the magnetic field changes. And then I reach a certain point of the magnetic field where you have this sharp transition. Okay? This is a property of what is called flux qubits, which they are different than plasma qubits. And you can assess by just the same instrument, but by just looking at the resonator. So you don't even have to excite the qubit. You just modify the magnetic field and you keep looking at the resonator. And at a certain point, there will be a change. And the fun part is that this is periodic. So not only you have this avoided level crossing, but it will have a periodicity with the magnetic field. So you can go on. If you have a big coil, you can keep doing it forever, and you will have this periodicity. So this is, for example, how you check if a flux qubit is alive, which is what you will use for a quantum annealer. But transmon is used mostly for digital quantum computing. Flux qubits is used more for analog quantum computing.
Okay, maybe I'm super ignorant, but this is to somehow check if you have a quantum system or if you have created a enough quality, whatever.
Yes.
When it comes to when you talk about the coherence and getting out the quantum information and a bit more
you want to see a spectrum.
Okay, good.
Okay, now you do a different thing. Okay, now you want to see the 0-1 transition of your qubit. Mm-hmm. No, this is the same flux qubit I show you here. Okay, so this one that I just showed. Then you're like, okay, I want to know where the qubit is. Okay, I know where the resonator is. I know that the resonator changes with the magnetic field. Mm-hmm. So in this range, where you change here, you can take this magnetic field and say, okay, now I will check this magnetic field here. And this time I send exactly the frequency of the resonant frequency. Okay, but then I add the pulse that scans. So you start and you say, okay, I send this. Let's say this is 7.5 gigahertz. Okay. And then I sum another pulse that is a 0 gigahertz. And then I do 0.1 gigahertz, 0.2, and then I go up to 8 gigahertz. And at a certain point, you will see some points that are different, And if you do the whole scan with the magnetic field, this takes one night. It's not actually it takes 1 hour. You will start seeing that you have exactly this 0-1 transition. And if you go at higher power and higher frequency, you will see also the 1-2, the 3 transition. I don't know because some are forbidden, but you will start seeing transition. Okay. So this is, for example, how you measure a qubit spectrum, which is still in the characterization because this tells you that the qubit is alive. This tells you that the qubit is alive and has a minimum energy of certain gigahertz, which you would like to be above 1 because your thermal excitations are heavily suppressed until 1 gigahertz, and then 20 millikelvin is around 1 gigahertz. So then you start having a qubit that is very annoying in thermal excitation. And then if you want to do this one, well, there is more complicated measurement. I didn't have time to call it. So you can start with the qubit in the ground state, for example. Then you can do certain measurement where you understand how much voltage you have to send in and how big. So when you do the arbitrary waveform generation to excite the qubit, you basically can pick the size of the pulse in time and the height in voltage. So you can calibrate this, and then you can figure out how big as an amplitude and for how long you can send a pulse to excite the qubit to the excited state. And then what you do is this. Okay, the procedure is this: you have the qubit in ground state, you send the pulse to excite it. No. Okay. Then you wait 1 microsecond, and you send what is called a readout pulse. So you interrogate the resonator. Again, if you go back, we know that the resonator will change its state if the qubit is in the ground or the excited state. So you will not interrogate directly the qubit, but you will check the residue. Okay? It happens like this. You send a pulse with a certain shape to excite the qubit, and you know your qubit will be excited. Then you interrogate the resonator after 1 microsecond. And the resonator will tell you, so you repeat this 50,000 times, and your resonator will tell you, yeah, the qubit is still excited. You know, it's 99% excited. You know? Sometimes you lose. But then if you then wait 50 microseconds to interrogate the resonator, and you repeat this 50,000 times, let's say, well, now it's 75%. And if you wait 100, well, maybe now it's 40%. And if you wait 150, it's 25. And if you wait 200, it's 0%. So this is how it works. For example, this is what it tells you, not only that the qubit is alive, but that the coherence time of your qubit has a certain time. So this will be more or less, I don't know, 100 or 70 microseconds. Depends. There is a definition depending on the decay.
Just to be clear, these measurements are tests of the quality of the qubit's
Yes.
manufacture and its environment, not doing any evaluations that would be useful.
Yes, but it's very important because if you have a low coherence time, you cannot perform calculation. So, for example, when I said before, D-Wave is very famous in the quantum annealing, but it makes dubious quality qubits because they have qubits that they have 2,000 qubits, so they make a matrix of qubits. They are entangled, let's say, with their neighbors, but individual qubits have a coherence time of 10 nanoseconds. So you have to perform your nanoseconds. So you have to perform your calculations super fast. And actually, they show papers where they actually are limited by how bad is the quality of the qubits. So the whole project that the PI of our group started is because they want to flip and say, okay, let's make fewer qubits, but with higher coherence, and then see how much we can really do if you want to do quantum annealing.
Why do they need to have coherence time in the milliseconds compared to?
No, it's not in a millisecond. But if you have 10 nanoseconds, it means you have to, okay, coherence 10 nanoseconds means that if you have 1,000 qubits, okay, well, there is a probability, no? So it's not that every single qubit will decay after 10 nanoseconds. Some will decay after 1, others will decay 20, so it's a mess. Okay? And you have to perform your calculation in 10 nanoseconds, which is, it's hard. I mean, that is going to be your limit. Instead, if you have a longer, then you can perform a calculation. So consider that, I mean, at a certain point, I can go back, but I show you that, I show you that we have a computer sending the signal. So, I mean, there is even a time just to send a pulse. So we have to send the command, and then the software has to do all the processing. In fact, now many people are moving in the, how's it called?
FPGA?
Yes.
FPGA.
FPGA programming directly. So without passing through all the steps, because, so now what we do is like, okay, computer says send a pulse, then it goes to the cable, start, send a pulse. And then say, you have to send another pulse, it does all this stuff.
It's because quantum computing is inherently necessarily slower than traditional manual computing, or because of all the structure that needs to be around it for this to work in this current.
No, it's because if you have a transistor, you put it in one, it never decays. If you have a qubit, you have the clock starts running, and you have to say, okay, I have a system that I want to perform calculation with, but it's going to decay in a very short time. So I have to be fast. I have to find a way that I can manipulate the system in a way that it doesn't do weird stuff, it doesn't have the coherence, and it gives me a solution to my problem that makes sense. So that is the big problem.
So about the quality of the qubits. First, the competitors, the D-Wave, like what makes them so bad? And also what kind of things are you looking into solving? Are you assisting mostly material science or?
So just to clarify, we're not competitors to D-Wave. D-Wave is massive compared to us as a credible resource. But let's say D-Wave was not that to sue me, but so D-Wave focuses very heavily on the amount of qubits, because of course that, you know, even from a commercial point of view, saying I have a 2,000 qubits is more attractive. And also it's also true that you need a lot of qubits if you want quantum processor. It's not that you would not get away with 5, even in quantum annealing. But then they put it level where they needed to do a fabrication that allowed them to make a lot of qubits. And let's say I would say their fabrication technique I would characterize as brutal, because they basically do a stripe, and then make other stripes, and they have massive Josephson junction, which means a lot of defects, and then the quality is low. So instead, what we want to do is to make more complicated design, more entangled qubits, and it's not ours only. I mean, in MIT, they actually went up to 25 coherent flux qubits, for example. And still, it's hard, because then you have to control this. So, okay, I said, so traditionally, they say the transmon, you can send logic gates. In the quantum annealing, you don't. But what you do is you manipulate locally the magnetic field, for example. So you have to imagine that you have to have a way to make a qubit A communicate with qubit C, a qubit C communicate with qubit D, but then sometimes you have to shut down this communication. And this is all done by controlling the magnetic field locally. So this means that every time you add a qubit, you start adding more connections, and then you have a more complicated software. And in the end, for example, I don't know how D-Wave does this, because they sell a processor that actually can handle this. But the MIT group that tried to make a coherent qubit, for example, they had to do a picture with a machine learning technique to find which fluxes to send to each individual qubit, and it gets out of hand very quickly. So since we are a small lab, we wanted to stay at 5. 5 is it's already hard, but it's a reasonable amount of coherent qubit where you can start playing around, maybe simulate some very easy molecule or very easy atom and play around.
From your last comment, did you identify any particular problem that you think that, because I understand you're focusing on the physical fabrication of the device and the materials. So I'm wondering if you, for instance, do you have any collaborations with the Institute of Nanotechnology beside here, or are you developing any kind of cooperation with other institutions that are focusing on these machine learning techniques or processes?
I mean, we usually collaborate a lot with CNN. Well, I don't know, but then also we collaborate with ICN2
here, right?
Yes, and then ICN2, and then also ICFO. So we use infrastructure. We use.
Yes, because I remember that the ICN2 they came here and they told us something that was probably related to this, because this was a Horizon Europe.
Yeah, maybe it was the same. I'm not sure. But yes, so I mean, this is to a scale that is very hard for us to really be competitive, in the sense there is many people involved in this that have much better resources, and still the problem is not clear. The solution to the problem is not easy. But of course, I mean, we are doing our own fabrication, so in the end, sometimes we implement our own techniques to try to address certain problems. And since we work in this field that is flux qubit, that is a niche field, let's say that there is less people really focusing on improving this type of qubits, while for transmon and
do you have any open problems that you think that could be solved with machine learning?
Well, if you manage to do 5, 6, 10 qubits, as I said, you need to use machine learning to basically control them.
So it's better quantum machine learning for quantum control.
I don't know if it's quantum machine learning, but you need definitely some machine learning to understand how to perform the measurements, because in a human mind, I think it's a problem, because as I said, that you have all the combination of possible pulses or possible magnetic field, let's say, changes locally, and this is hard. So for example, maybe you want at a certain point to have 3 qubits communicate to each other, and then in a certain moment you want to evolve, this Hamiltonian, and then you have to start opening another qubit or do some weird processes. And all this is done by local magnetic field changes, which in the end is just a pulse of some current. It's nothing fancy. It's just, but then if you start plotting all the possibilities, you literally have images with that look like fractals where you have to go around and check. So if you want, I can forward the paper. I don't know if you have it published. Quite insane.
You had this timeline near the beginning of like the 3
Yeah.
and how maybe we verify. I don't know much about quantum computing algorithms, but how many do you need before you start being able to perform the kind of calculation or computation that starts giving really serious results that we couldn't do with traditional computation?
So,
How big does it need to be useful, I guess?
so there is a concept, I don't remember, it's a noisy, intermediate scale quantum computer, noisy, something like that it's called. So there is, if you want to look, it's called a noisy intermediate scale quantum computer, so you can check what they want to do. As far as reply is, what they show was for transmon, or let's say this digital quantum computer. So if you want a quantum computer that is error corrected, you need around 1 million. And there was this paper recently in November or December that made a big splash, and it sounded very good because they said, the more you scale up the device, the less error correction you need, more or less qubit you need, and this basically confirms this projection. So in a sense, yes, it's true that you need less, but it's not that you need fewer than you anticipated. It's just that everything is going as you mentioned, so you need 1 million. In quantum annealing, we don't know, because the best, as I said, the best processor in number of qubits is D-Wave, but they prove that they are limited by the coherence of the qubits. So until someone comes and makes a 2000 qubit with coherent qubits, it's going to be hard. But the idea is that, of course, there is also the big different philosophy in the sense that digital quantum computing can solve any problem, and quantum annealing can solve certain specific type of problem, like sure. But they are still useful.
Can I ask something more?
Sure.
To modify you change the magnetic field, and I understand this has like there are two motives for which you want to make this. First, to measure, and also to control the Hamiltonian that controls the qubit. To modify the magnetic field in this coil in the cavity, you put a different current. How does it work?
So there is two.
Because you could modify the coil as well, no?
No. Yes. So there is two concepts. Sorry, I'm going there wrong place. So you have so yes. So this is the coil. But I don't know if I can go back to the. But it will take a while. But there is the local and the global magnetic flux. So if I get back to the chip, I'm going to show you what I mean. Here. So the coil is placed outside the box. So this means that when you modify the magnetic field, you change the current of the coil, and you modify the magnetic field for every single qubit. Then you have the type of flux lines. Here you can send, so as you see, the feed line, so input output, is basically filtered by the resonator. So the resonator that acts as the qubit is in between the feed line where you send input and output and your qubit. But then the flux instead is directly coupled to the qubit. Okay. So this means that we do not really read the qubit from here, but this is only used to modify locally the magnetic. For example, if you want, this is not as, so this is a prototype. So this means that we are testing single qubit to check how good they are. They will not be in this configuration. No? They will be that every qubit has a way that is connected to the other, and then we'll have a similar flux line that you can basically turn on and off to make them talk. Okay. So one thing is the global flux that you modify with the coil, and that is used to do the first what is called spectroscopy or some assessment if the qubit is alive. But then if you really want to use the qubit, you will have to use this. And this you just send a very tiny amount of current, and this will change locally the magnetic field. Now, if you understand a bit how this works, it means it's also a headache because there is going to be crosstalk. Because magnetic fields are very hard to confine properly, so that's also another problem of using this system. That you also have to minimize the crosstalk between the local flux line and any spurious magnetic field, and this is hard.
You said that you wanted like a super good connectivity, etc.
Yes. So this is terrible because this is
yes.
not
How does it look like qubit 0 to qubit 7?
So usually you have what is called coupler,
Okay.
which is, well, basically a qubit, but different. So a coupler, I don't know how people do it, but you can do it with what is called a squid. And a squid is a loop with two Josephson junctions. And okay, the short story is that you can open and close this coupler by no. So it's basically the same. So it's so you will have the qubit 1 and qubit 2. Then now you put a line here, and then you make a Josephson junction with a loop with two Josephson junctions here, and then another flux line. And basically, what will happen is you can manipulate the flux that is connected to this coupler to open and close the coupler. Mm-hmm. And of course, if you want 5 and you want to have all interconnected, well,
it's a mess.
It's a mess. And this is exactly what I'm saying. When you go up in quantum annealers, it's true that they need less qubits, but if you want to make them talk to each other and you want to control properly, then the flux lines scale up like crazy, like exponentially at that point. So either you go by approximation, you start saying, okay, maybe I have which is what the wave does. So the wave makes a matrix, and then they only talk to their neighbors, and that's it. So the interconnectivity is not there. So if you want a really high interconnectivity, you start to have to do a bit of creativity. And in fact, the solution to this is that you start to make flip chips. So you will have a bottom chip and a top chip, and they are just talking through wireless, basically. So one part of the chip will be with the qubits, and the other part of the chip will be with the couplers and readout, and then you start doing this weird, and it gets harder and harder. So.
But correct me if I'm wrong. That means that if you are having these couplers here, that means not only those qubits that are physically close to each other are being able to generate.
So the idea would be to do for everybody. Yeah. So for every single qubit should be connected in a way to another qubit, and you will be able to connect 1 and 5 and 3 and 2. But then maybe if you want to shut up 2 and 3, and this many combinations that you can do.
Do you have any pathway in your research that, or is this?
Yeah, this is what I mean. A coherent quantum annealer with 5 qubits should do that. Should have all the qubits connected.
But it is not now.
No, this is just, as I said, this is just test prototype. So they are actually all disconnected because, as you can see here, they have no path. But in theory, the final design will be that they are all connected. So you can make a ring, or you can make some star, some weird stuff. I don't know. We didn't get it there.
And can you look at it without 3D?
What does it mean 3D?
So it's not like a.
Well, I show you that we have this. Well, no.
The aluminium.
Yeah, this is a 3D. No. So, for example, this is. I don't know if it's what you mean, but okay. This is a planar, no? This is a 3D in the sense that you don't have a resonator here. Your resonator is the cavity. So that
okay.
So
yes.
You don't need
more like if you can put like if you have some chip that are connected to the neighbors.
Yes, exactly. This is the flip chip technology.
Like
yes.
Up.
People do 2-3 stacks. They do what is called bias. So they can do holes in the silicon where you can bring the current down, or you can just, as I said, you can do flip chip, and then you can do what is called bump bonding, where they are just connected to the ground, and then they basically work in a wireless fashion. So there is things like that.
I have 20,000 questions, but I maybe one final more. But just okay. So for us that we live a bit in the bubble of theoretical physics and whatever, when we think of these experiments and this stuff, like we have this word open quantum systems, and then some sort of magical solution which is like this is Markovian and whatever, and then we have the Lindblad equation, and then when you measure and you have this continuously monitor quantum systems, and then you have the Bible of this topic, which has the cover of a superconducting qubit and this Josephson junction or whatever. which is this book of Milborn. Well, so my question is, how much do you use this formalism in your daily life? You don't.
Barely see equations in my life.
Okay, okay.
But yeah, but I mean,
So you don't
so,
have
okay,
math
but this is-
equations in your.
let's put it like that. It depends what you're doing. Okay, so okay, if it's not too long, I can give you. So the thing is works like this. So you start with theory, and you do basically you quantize. So you draw your circuit by pen and paper, and you start to do the quantization, which I don't do, but people do it. Other people design the shipping group do that. So they start from they write down the Hamiltonian of the circuit, they do all the quantization, and this is the paper and pen. No? And then from there, you have to translate it to a metal or to some structure that is, that you can actually make with the machines. And then this is what you do afterwards. So there is a part that involves, I just don't do it, but there is a part that involves theory, which is exactly the circuit design. So for example, if you go to Kilimanjaro, the company, they have a theory division, a software division, a design division, a hardware division, and every single subdivision is involved in different aspects. So if you say, I want to have a quantum annealer with 5 qubits, and okay, you say, all right, how do we improve coherence, for example, or, and then you say, okay, maybe we have to put many Josephson junctions, and then you start to make a fluxonium qubit, which is a different type of qubit. Or you can say, okay, I want to have a qubit that has a 0-1 transition at the sweet spot. Well, so the minimum has to be at 2 gigahertz. No? So then you have to calculate, paper and pen, making the simplest diagram you can, how you can make it. So for example, the ones I showed you before, so these, yes. So these, first for example, there is what is called optical layer, which is basically a resonator, big structures, So you first have some simulation, and that tells you where the resonator will be, because also you have to do that. And you have to take into account that he's a superconductor, so you have to use also all the equation that involves superconductivity to, for example, calculate the kinetic inductance. And so this is the easy part. And then you want to do the qubit part. I have the loop here, so I can show you, because it's nice. No, please. This one. See. For example, the PhD that designed the qubit I show you figure out that is 4 Josephson junctions is what he needed to achieve all the parameters that we wanted. So the parameters you want, for example, is how much supercurrent flows through the loop, what is the minimum energy of your qubit, what is the coupling between the qubit and the resonator, all these kind of things. So they are done both pen and paper in the Duro quantization, and then also in simulation with the specific software to see, when you put metals and you put a real thickness and you put a real distance, how much actually you can get to there. And then the third step, which is what I mostly do, is then I test and I say, okay, yes, we hit the parameters or we don't hit the parameters. But there is a part that is absolutely, so now there is tools, I don't know if it's called Qiskit or something like that. There is tools that even do, you can put the elements and they give you the Hamiltonian, if there are some standard sequence. So you can just put a transmor qubit or put a Josephson junction and a capacitor, you set your numbers and they give you the Hamiltonian. But I never use those, but I know they exist. So, I mean, there is for sure a lot of theory involved, and it's hard, but it's very hard to do everything. So.
Yes, sir. Well.
And from the previous version, is there any hot problem that you are having that has to do with machine learning, for instance? Because I don't know if we are before the communication center,
Yes.
We are knowledge computer vision. However, most of the things that we are doing to do with deep learning and to machine learning, reinforcement learning. I
think BSC will have this problem soon. So BSC will have this soon, because the point is exactly what I said. That the way I see machine learning into superconducting qubits is, how do you control a system that is exponentially getting harder, because this is the point. I mean, BSC now they will start to have a 10 qubits quantum annealer. Okay, the first iteration will be maybe simple because they will do certain design. But then when they go up to 20, 25, 30 qubits, if it works and everything is well, how do you start controlling this? So they will have. Kilimanjaro won the tender, so Kilimanjaro will provide probably some software. But I mean, this software, I don't see how they get rid of. You need machine learning because it's going to be very hard to just implement it in a traditional logical way. Because, as I said, you start seeing this, so that you will have, for example, many minima, it's not going to be a single point, So it's not going to be a single solution. So you will have to figure out a way also to do to send pulses automatically, to do routines where you just check, for example, that your qubits are all well and stuff like this. So it's for sure a lot of room when the system gets complicated. When you work with single qubits, of course, but well, if you get to 5 qubits, I will assume that you start already having headaches. But also we are going to collaborate with BSC. We will have to find a way to do benchmarking. So, okay, let's assume I contract you and say I give you 5 million euros, you deliver a quantum computer, a quantum annealer, And then you give me a quantum annealer. Okay, how do I check that this quantum annealer works? I need to encode some basic problem that tells me how good is the performance of the hardware you deliver. Already this, I would say, if it's complicated enough, you probably need machine learning.
Well, I mean, yes, there is no guarantee that machine learning will work at all. But yes, it's a. I think that Tony and Martin, they have a super cool project which is very related to this, which is actually using machine learning or some techniques to. You mentioned this general waveform or general
arbitrary waveform.
General mixer. Arbitrary
waveform generator.
Waveform generator. Yes. But I think so. We were discussing some possible overlap to some little project or whatever. But I think it was more related to compile a digital gate, right? Like to compile a rotation or
control of the.
Yes. But this is
which is very similar.
It's the same in the sense, okay, yes. One you make gates, and the other you control the magnetic flux, but in the end,
it's controlling the component of the system to evolve with it.
Yes, and to do so, you have to send short pulses. You have to send. It's in the end is I see that you just change a bit the tools, but in the end, I think it's similar in the sense you have a very complex system that you have to control. And yes, I don't know how they will do it because I saw the presentation of MIT group with 25 flux qubit, and I was like, this is
what I feel
it's a headache,
is that there might be a lot of room for machine learning in this material design for different superconducting materials. Like you saw one other material that you explored that has a higher critical temperature.
Yes.
And I had the feeling that you were kind of blind exploring, okay, yes, let's put a bit like an alchemist.
Well, it's not blind because you know that, let's say, this should work. So they do that in the oxygen environment or something. So they do with other gases. So you know that in theory, this aluminum can be changed. But what I would think, so the application would be maybe more now it's still a lot of paper and pen to just design a qubit, That should be in some way automatizing in a certain way, because then this should be Hamiltonian. In theory, you should be able to add elements in this. You should be able to, but it's still it's still done.
Yes,
it's not trivial at all. But
you need a lot of data for the most basic algorithm machine learning. You need a lot of data and experience.
Yes. No, but I'm saying literally how you design the device. You say, okay, I put a qubit here and I put a resonator here, you know, but you still in the end rely on simulation. Even if it's just ideal system, which is, as I said, there is now tools that they provide you an Hamiltonian by just adding elements, but I think this can be explored much more, because if you really want to be serious and start making a quantum processor with thousands of elements in a like a you know, when you open your computer and you have a motherboard, your circuit is quite complicated. It's not. So I don't know how they do it, if they really do it by hand, but I hope not. Because
when you produce the qubits, can you simulate the properties of the qubit from the like DFT calculation?
so we do both. Usually before you produce a qubit, you simulate all the properties, then you test it, and sometimes we do the opposite. So we measure and then we roll back and we try to find out actually how it is behaving. So, well, we don't do it ourselves because we have other people that it's more involved in theory. But sometimes you can give data and say, okay, can you figure out how it is this qubit behaving now? Because we just see this and it's not as we simulated. No?
How do you characterize the qubits? Like, do you, for example, use them?
Yeah. So, well,
What?
Sam, you said Sam? Yeah. So there is different ways. So, okay, you measure it first of all. So usually you can do SEM, which is basically electron microscopy. So you look at the structures. So these, for example, once a qubit is, so this is quite invasive because you're literally throwing electrons at the sample. So when the qubit is expired or it doesn't work, you can literally have a look at it. In fact, this is a SEM, that's a SEM image. So yes, you can even measure the structures to check that everything is right. You usually in the chip you fabricate, you make some what is called test junctions. So they are similar in structures, but they are on the other side that you cut away from the chip, and you can check that the currents are okay. So the structures are connected, that they have oxide, that they like they behave like a just junction essentially. And then, and then you do the measurement. This basic measurement I showed at the end, which tells you if it works. For sure, I mean, we do a lot of post-mortem analysis. Most of qubits don't work, so you actually, this is the reality.
It's super interesting. Like, wow.
So let's summarize. You're working close to absolute zero with no cosmic rays at all. Basically, maybe almost in the pure void. You cannot interact with your devices with electrons because you don't fry them.
Yeah.
And
you have to use gloves because otherwise you fry the qubit. You have to use the ground, like this. You have a bracelet that grounds you because you might kill the qubit in the ground.
well,
They cannot even have an electrical discharge.
you're not having a white room, right?
Yeah. Everything is in clean room. Everything's fabricated in clean.
Fully clean.
Yeah, when the fabrication, yes. Then
I mean, when you have deployed the quantum computer with all the cooling.
no, this is not clean. That will be too much. But yes, it's at the limit of every single technology you can imagine. It's at the limit. It's at the limit of fabrication. It's at the limit of material science. At the limit of cryogenics, vacuum. It's interesting because it's really like you're pushing to. You do not have much more room than this. That's why I'm like. When you say you're competing or not competing, but you are your competitors, like our competitors, the electron beam lithography machines, they cost 10 million euros each or more. So this is the scale. Yes, we use it because we have now CNM or ITFO or ICN2 that buy them for the whole community. If you would like individually want to build a qubit, you would have to spend maybe 30 million euros alone. So this is not for one qubit. It's not.
Yeah, for one qubit.
It's not an easy task.
And Kilimanjaro is way beyond that budget.
But Kilimanjaro, no, because I mean Kilimanjaro
Way below.
is below because they don't
Yes,
have
yes.
they don't have a clean room, they don't have a BL, they still rely on external. They have a lot of people. So this is I don't know if they are 50, 70, there are a lot of people. So
Well, but I mean, these quantum startups, they raise like 100 million euros.
yeah, I don't think Kilimanjaro is that much, but but they have 4 fridges, they have theoretical software, hardware division. I mean, they do a lot more stuff than we do. But I mean, it's hard. It's really hard. Especially fabrication is really at the limit of everything.
Ultra cool. Well, thank you.
Thanks.
Thanks for the invitation.
This kind of talks are well super appreciated because there is like an audience